problem 5 says, a car is traveling on a straight road at 9 meters per second, goes over a hump in the road. The hump may be regarded as an arc of a circle of radius 11 meters. What's the apparent weight of 600 Newton woman in the car? She rides over the hump. So here we go. So here is my road. And there's like this hump in the road, right? And this hump is part of a great big circle. Okay? All right, sort of thing. All right, this is all underground, right? Okay, but that's an arc of a circle of radius 11 meters. Okay, and the car is traveling along. All right. Okay, and we're buzzing along here at 9 meters per second. We're looking at when we're at the top there. Okay, and the question is, what is the apparent weight of a 600 Newton woman who is sitting in the car at that point? And so you say, well, if I think about the forces acting on the woman in the car, right? Hey, look. There she is, okay? You'll say, well, I've got a gravitational force. It's my ranged force. And then contact forces, she's touching the seat. There's going to be a normal force pressing up on her from the seat. And that's all we have. We're going at constant speed. We don't have any acceleration tangential here. We're going at constant speed around the circle. So you say, okay, they want the apparent weight. So we will recall that mg, how hard the Earth is pulling on you, that is your actual weight. Okay, how hard the Earth pulls on you, that gravitational force, that is your weight. But your apparent weight, or your perceived weight, how heavy you feel like you are, has to do with how big that force is that's supporting your weight. Okay, now what's supporting the woman's weight is that seat pushing up, that normal force. That is going to be the apparent weight. That's how heavy you feel like you are. If the seat's pressing really hard on you, you'll feel like, oh my gosh, I'm being jammed into that seat by gravity really hard. I must be really heavy. If the normal force is really small, then you'll feel like, oh, not too heavy. The chair's barely pushing on me, right? So that's the idea. So we're trying to solve for the normal force, and we're trying to solve for apparent weight in this case. If I had a problem where I was like hanging by a rope, then that tension in the rope would probably be the force that was supporting my weight, and that would be my apparent weight, would be that tension. But anyway, get back to this. So apparent weight is that support force. So we say, all right, I recognize right away, because this is a circular motion unit, you're like, hey, these forces are along the radial axis. I'll bet that just like every other circular motion problem, I want to look at the sum of the forces in the radial axis to be mass times acceleration centripetal. In the radial axis, how am I going to write this? N minus mg, mg minus n. Well, we're going to do forces in minus forces out. That's the rule. Toward the center of the circle has to be the positive direction. You don't have an option. So it's going to be mg minus n is mac. And ac we could substitute if we wanted. We could substitute in v squared over r. Don't mind if I do. All right. And we're trying to solve for that normal force. And so we say, well, in this case, just look at the picture. Is n going to be bigger or smaller than mg? Well, I know that my total force has to go inward. I'm moving along this way, and I want to turn myself this way, right? As we go over the hill, I need a total force to be bumping me inward. So mg had better be bigger than n. Our apparent weight is going to be less than usual. It's going to be less than mg. So, and if you check it out, you say, oh my gosh, if this is less than mg, I'm going to get a positive value here. That's good, because this has to be positive. Mass is positive, radius of the circle is positive, speed squared is positive. So the total always has to be positive in the radial axis. That's why it has to be inward. So look at this. Hey, I know the values for everything here. Rearranging, I'll have n is mv squared, like I was saying, mg minus mv squared over r. You didn't see that. Okay, is going to be n. And so again, if I was sitting still, the velocity would be 0. Oh, look, n would equal mg. right? If I was just sitting still or going at constant speed. But because I'm changing my velocity, going to curve, I need a net force to do that for me. So putting in my values here, she is 600 newtons. What does that mean? That's the weight. That's the force. So this is 600. My mass, though, they didn't tell me that. But the weight is 600. So that's m times 9.8 equals 600. So 600 divided by g, divided by 9.8 will be m. You see that's how I got the mass? And then v squared over r, the velocity is 9, and the radius is 11. So if I take my calculator and I punch in and I say, hey, we're going to take 600 minus 600 divided by 9.8 times 81 divided by 11, my calculator says, hey, that's 149.2, sure, why not, rounding here, newtons is the apparent weight. You say, look, her actual weight's 600. This is about a fourth, right? 150 would be a fourth. Like she weighs only like a fourth of her usual weight as she goes whipping over here. You would totally feel those butterflies in your stomach whipping over this hill like that, right? Okay. And you've probably experienced this yourself, going over maybe like a railroad crossing, right? Real fast, which is probably rough on your car, or maybe going a little too fast down Book Road south of 75th, right? Was that quick drop? Or maybe on a roller coaster. Like maybe you go down a big steep hill and you're going fast, and then you go over a hill and you go, woo, right? And you feel your stomach, feels like stomach rises up because it's not being pressed down in your body by gravity as hard, right? Because you know what I'm saying, it doesn't feel, it kind of loosens up. Anyway, moving onward. So that's that. Okay, now that's just part A. Part B now says, hey, now you've done that, what if we're going to have, what would the speed have to be now if we wanted to feel weightless, right? Now, not true weightlessness. There's still gravitational force. That doesn't change. But you're going to feel weightless. We want your apparent weight to be 0. And so you say, oh, we need the normal force to go to 0. So I'm just going to take this guy, right? But I want that normal force to be 0 because I want to feel weightless. Now, this side was equal to mg minus something. But now I'm not going to subtract off. This is going to be bigger than it was before. Now, the mass isn't changing. The radius of the turn isn't changing. The speed is going to make this bigger. The v's got to be faster. Makes sense, right? I'm going to whip over that hill even faster. If I whipped over the hill fast enough, I would lose contact with the ground and fly, don't you think? What would be my apparent weight when that happened? I would feel weightless. I wouldn't be pressed in anymore, right? And me and the car would lose contact with the ground. The normal force would go to 0. This is the speed where you lose contact with the ground. Okay? So anyway, looking at this, now I got mg is mv squared over r. Now, this term is gone, right? That's gone. Now I've got an m in every term. So now I can divide through by the mass, and the mass goes away too. Sweet. And so I'm going to have just g is v squared over r. Move the r over. The square root of grr is v. That's going to be the square root of 9.8 times radius of 11 meters. Punch that in my calculator, and you say, hey, the square root of the quantity 9.8 times 11. My calculator says, hey, that's going to be about 10.38 meters per second. Is that magical speed where I will feel weightless. Ta-da! And if you went any faster, you would be leaving contact with it and flying over that hill. Which, of course, this is, of course, a dangerous thing to do. I should just say, I feel obligated to point out, you know that the way you steer and the way you brake, it has to do with having friction between your tires and the ground. And so if you do not have a very large normal force, right, then you don't have a very large friction force, and you cannot turn quickly to avoid something or slow down quickly, right? And so when you're doing this, you are putting yourself in a situation where you don't have control over a vehicle, which, again, to make this happen, you are going relatively quickly probably, right? And so you say, that's a recipe for disaster. So I am not, let's make this clear, I am not endorsing this behavior. Experience it on a roller coaster. Okay, moving onward. So that is problem 5.